States of Matter Part 2. This video is beneficial for Class 11, JEE, NEET and KVPY. Let us begin. Graham's Law of Diffusion. Diffusion is the tendency of any substance to spread throughout the space available to it. Effusion is the process of any gas molecule coming out of the container through a small orifice due to pressure difference between container and the surrounding atmosphere. The process of effusion is similar to diffusion and same formula are applicable with only difference that effusion occurs due to pressure difference. According to Graham, the rate of diffusion or effusion of gas at constant pressure and temperature is inversely proportional to square root of its molecular mass. Or we can say that R1 by R2 is equals to under root M2 by M1. Molecular of molecular mass of gas is equal to twice into vapor density. R1 by R2 is equals to root D2 by D1. Now a question. The densities of hydrogen and oxygen are 0.09 and 1.44 gram liter inverse. If the rate of diffusion of hydrogen is 1, then that of the oxygen in the same units will be. Here, rate of diffusion of oxygen is equals to rate of diffusion of hydrogen into under root of density of hydrogen upon density of oxygen. After putting the values, we will get rate of diffusion of oxygen as 1 by 4. Therefore, according to Graham's law of diffusion, at constant pressure and temperature, V1 by T1 into T2 by V2 is equals to root D2 by D1, which is also equals to root M2 by M1. D1 and D2 are respective densities, and V1 and V2 are the volume diffused or effused in time T1 and T2. N1 upon T1 into T2 upon N2 is equals to root D2 upon D1, which is also equals to root M2 by M1, where N and N1 and N2 are moles diffused or effused in time T1 and T2. X1 upon T1 into T2 by X2 is equals to root D2 upon D1 is equals to root M2 upon M1, where X1 and X2 are distance travelled by molecules in narrow tube in time T1 and T2. Now a question. A bottle of ammonia and a bottle of dry hydrogen chloride connected through a long tube are opened simultaneously at both ends, and a white ammonium chloride ring first will be formed when we know that NH4Cl ring will first formed near the HCl bottle because rate of diffusion of NH3 is more than that of HCl because molecular mass of NH3 is to molecular mass of HCl is 17 is to 36.5. So NH3 will reach first to the HCl bottle and will react there with HCl to form NH4Cl ring. And now we'll move to kinetic theory of gases. A gas consists of tiny spherical particles called molecules of the gas which are identical in shape and size. The volume occupied by the molecules is negligible in comparison to the total volume of the gas. Gaseous molecules are always in random motion and collide with other gaseous molecules and with the walls of the container. Pressure of the gas is due to these molecule collisions among themselves and with the walls of the container. These molecules are elastic in nature. Molecular attraction forces are negligible. For an ideal gas, attractive or repulsive forces are equal to zero. Effect of gravity is negligible on molecular motion. PV is equals to 1 by 3 mnu square, where m is the molar mass, n is the Avogadro's number, and u is root mean square velocity. For n moles, average kinetic energy is equals to 3 by 2 nRT, and for 1 mole, average kinetic energy is 3 by 2 RT. Average translational kinetic energy per molecule is 3 by 2 R by Nt, which is equals to 3 by 2 kT, where R upon N is called the Boltzmann constant. Its numerical value is equals to 1.38 into 10 raised to power minus 16 ERG Kelvin inverse, molecular inverse. Thus, average kinetic energy is proportional to absolute temperature. If T is equals to 0 Kelvin, then average kinetic energy is 0. Maxwell-Boltzmann distribution curve. At a given temperature, the velocities of a gas molecules may have any value between 0 and infinity. The number of molecules having speed 0 and infinity is very small. The number of molecules with most probable velocity is the maximum. At a given temperature, the area enclosed between the curve and the velocity axis represent the total number of molecules. At a given temperature, the velocities of different molecules are different. The number of molecules with higher velocity increase with increasing temperature. Now, different types of molecular velocity. First is the root mean square velocity, URMS. It is defined as the square root of the mean square of velocities possessed by all molecules present in the given sample of gas. URMS is equals to under root u1 square plus u2 square till un square by n. URMS root mean square velocity is equals to root 3 PV by m, which is equals to root 3 RT by m, which is equals to 3 P by D. D here is the density. If N1 molecules have velocity u1 and N2 molecules have velocity u2, then URMS is equals to N1 u1 square plus N2 u2 square upon N1 plus N2. Average velocity UAV. It is given by the arithmetic mean of the different velocities possessed by the molecules of the gases at particular temperature. U average is equals to U1 plus U2 till Un upon n. U average is equals to under root 8RT by pi m. Most probable velocity UMP. It is defined as the velocity possessed by the maximum number of molecules of a gas at a given temperature. UMP is equals to root 2RT by m. If P and T both are given, use equation in terms of temperature. That is, use URMS is equals to root 3RT by m and not root 3PV by m. Relation between RMS velocity, average velocity and most probable velocity. URMS is to U average is to UMP is root 3RT by m is to root 8RT by pi m is to root 2RT by m, which is equals to root 3 is to root 8 by pi is to root 2. Also, URMS is greater than U average and it is greater than UMP. Now, van der Waals forces. Van der Waals forces include attraction and repulsions between atoms, molecules, and surfaces, as well as other intermolecular forces. Now, real gases. Although the ideal gases model is very useful, it is only an approximation of the real nature of gases, and the equation derived from its assumptions, PV is equals to nRT, and are not entirely dependable. As a consequence, the measured properties of real gas will often differ from the properties predicted by our calculations. Now, difference between ideal gas and real gas. Ideal gas obeys laws under all conditions of pressure and temperature. Real gas only obeys at low pressure and temperature. Ideal gas obeys ideal gas equation, and real gas does not obey ideal gas equation. Ideal gas intermolecular interaction between gaseous molecules are negligible, but in real gases, intermolecular interaction between gaseous molecules are not negligible. In ideal gas, volume of particle is negligible as compared to total volume of gas. But in real gas, volume of the particle is not negligible as compared to total volume of the gas. Ideal gas exists only at high temperature and low pressure, but real gas exists only at low temperature and high pressure. Now compressibility factor. The extent to which a real gas departs from the ideal behavior may be depicted in terms of new function called the compressibility factor Z. Z is equals to PV by nRT. For an ideal gas, Z is 1 and it is independent of temperature and pressure. The deviations from ideal behavior of a real gas will be determined by the value of Z being greater or less than 1. For a real gas, the deviations from ideal behavior depends upon pressure and temperature. Here you can see graphs for the both. Here pressure, here temperature. From the previous curves we can conclude that at low pressure and fairly high temperatures, real gases show nearly ideal behavior and the ideal gas equation is obeyed. At low temperatures and sufficiently high pressures, a real gas deviates significantly from the ideality and the ideal gas equation is no longer valid. Greater is the departure of Z from unity, more is the deviation from ideal behavior. When Z is less than 1, this implies that gas is more compressible. When Z is greater than 1, this means that gas is less compressible. When Z is equals to 1, the gas is ideal. Now van der Waals equation. The equation of state generated by van der Waals in 1873 reproduces the observed behavior with moderate accuracy. For n moles of gas, the van der Waals equation is P plus n square A by V square into V by V minus NB, which is equals to nRT, where A and B are constants characteristics of a gas. This equation can be derived by considering a real gas and converting it into an ideal gas. Volume correction. For an ideal gas, PV is equals to nRT. In a real gas, the molecular volume cannot be ignored. Let us assume that B is the volume excluded for the moving gas molecules per mole of a gas. For n moles of a gas, the volume excluded is equals to Nb. A real gas in a container of volume V has only available volume of V minus Nb, and this can be thought of as an ideal gas in a container of volume V minus Nb. The van der Waals constant B, the excluded volume, is 4 times the volume of a single molecule. That is, B is equals to 4 times NaV, where Na is the Avogadro's number. Now pressure correction. Let us assume that the real gas exerts a pressure P. The molecules that exert the force on the container will be attracted by molecules of the immediate layer which are not assumed to be exerting pressure. It can be seen that pressure of real gas is less than the pressure of ideal gas. That means P is directly proportional to extent of attraction between the molecules which are hitting the container wall and the molecules which are attracting these. Features of A and B. For a given gas, the gas having higher value of A can be liquefied easily and therefore H2 and helium are not liquefied easily. The units of A is liter square atm per mole square, and that of B is liter mole inverse. The numerical values of A and B are in the order 10 raised to power minus 1 to 10 raised to power minus 2 to 10 raised to power minus 4 respectively. Van der Waals constant of attraction A is greater than the van der Waals constant of volume B. Now deviation by van der Waals equation. At moderate pressure, V is large and B is negligible in comparison with V. Then van der Waals equation reduces to P plus A by V square into V is equals to RT. This implies that PV plus A by V is equals to RT and PV is equals to RT minus AV. This implies that Z is equals to PV by RT, which is equals to 1 minus A by VRT, where Z is less than 1, or PV is less than RT at low pressure, below Boyle's temperature. This accounts for the dip in PV versus P isotherm at low temperature. At fairly low pressure, at fairly high pressure, A by V square may be neglected in comparison with B. Now the van der Waals equation becomes P into V minus B is equals to RT. This implies that PV minus PB is equals to RT, and PV is equals to RT plus PB. Z is equals to PV by RT, which is equals to 1 minus PB upon RT, where Z is greater than 1, or PV is greater than RT at higher pressure above Boyle's temperature. This accounts for the rising parts of PV versus P isotherm at high pressure. At high temperature, V is very large, so that both the correction factors A upon V square and B becomes negligible. Hence, at high temperature, real gases behave like ideal gas. Critical phenomenon. The phenomena of converting a gas into liquid is known as liquefaction. The liquefaction of gas is achieved by controlling pressure and temperature. Decreasing temperature. The decrease in temperature results in decrease in kinetic energy of molecules. In the graph, the gas shows signs of condensation and suffers an appreciable change in the volume, even when the pressure remains virtually unchanged. After the condensation is complete, then the change in volume with an increase in pressure is very small. Inside the dome-shaped curve, the liquid and the vapor exist in equilibrium. Now, methods of liquefaction of gases. On increasing the pressure, gas can be easily liquefied because intermolecular attraction between gaseous molecules increases. On decreasing the temperature, kinetic energy of gaseous molecules decrease. That's why gases can be easily liquefied. Third, temperature of gas must be lower than the critical temperature Tc. Now the Boyle's temperature. The specific temperature at which the real gases obey Boyle's law is defined as Boyle's temperature, which is equals to A by Rb. Now the critical temperature. The characteristic T for a given gas is below which a continuous increase in pressure will bring liquefaction of gas, above which no liquefaction is noticed, although pressure may be increased. Example: critical temperature for CO2 is 31.2 degrees Celsius. The critical temperature is 8A by 27 Rb, or it can be written as 8 by 27 into Tb. Now the critical pressure. It is defined as the minimum pressure applied on 1 mole of gas placed at the critical temperature to liquefy the gas, which is equals to A by 27B square. Critical volume. Critical volume Vc. The volume occupied by 1 mole of a gas placed at critical conditions. Vc is equals to 3b. Now the relation between Tc, Vc and Pc. Pc into Vc by Tc is equals to 3 by 8R. Value of A and B in terms of Tc, Vc and Pc are: A is 27R square Tc square upon 64 Pc. B is equals to RTC by 8 Pc into P.